Chapter 4 is the chapter that will begin our study of the dynamics of motion. The difference between this and kinematics is that, recall that with kinematics, all we were really concerned about was where the object was, where it was going, and we were describing that motion and modeling it with a series of equations that would tell us its position and velocity under the constant acceleration that it was experiencing. We didn't really ask the question, well, where does this acceleration come from, other than, we talked about the acceleration of gravity, and so obviously referred to the force of gravity, and so that led us to understand that gravity exerts a force, but we want to make that more general now and be able to relate any force that is applied to an object to the subsequent kinematical motion of that object and its acceleration and its position and its velocity. So we want to do that. We want to define what we mean by the concept of a force and show the relationships that were developed by Isaac Newton and that bear his name, Newton's laws. First of all, the concept of a force is really a push or a pull. That push or pull can be due to physical contact with the agent responsible for this push or pull, as in when you push on an object with your hand or pull on it by grasping it. You exert a force on it, don't you? When you lift an object, you exert a force on it. The push or pull can be mediated by some other object, such as a string attached to a ball, and then you pull on the string and the string pulls the ball. Same thing with pushing on an object with a rod or some other instrument. So you can have a mediating agent in between responsible for transmitting this force. Now, those are called contact forces, aren't they? Because you're actually in contact with the object that you're interacting with. We're familiar with other forces that are non-contact forces, such as gravity. You don't have to be in contact with the ground for gravity to act on you, do you? If you jump off of a chair, while you're in the air, gravity is pulling on you with its force, and you are experiencing a non-contact force. When you strike the ground exerts a contact force against you in the other direction, which brings you to rest or to a stop. So these are the kind of influences we're talking about. We'll oftentimes refer to these as the causes, because we're looking for the correlation between cause and effect that rules mechanical motion in our universe. Isaac Newton studied motion following on the heels of Galileo, and as a result of his studies and other work other people that had done, he put together three statements in his Principia Mathematica. And in this publication, he stated three, what we call laws now. They're called Newton's laws. They bear his name. And the first law is a two-part law. The first part seems somewhat obvious, and when you think about it, it will. An object remains at rest unless acted upon by a net force. What is the object we're talking about here? Well, it could be anything. Your coffee cup on the table, your shoes sitting on the floor. As you know, that coffee cup stays on the table at rest. And the word rest means not moving, not accelerating. So it stays there unless you do something to it. That means unless you come along and impart an influence to it, which we call a net force, a force that is remaining of all the forces acting on it. In other words, net means you add up if several forces were acting on it, such as one person pulling to the right, one person pushing to the left, and so forth. The sum total of those forces add up to one single force, and that's called the net force. But again, the idea is that unless something comes along to influence your coffee cup to move it, it's not going to move on its own. So you might say, well, that doesn't really take a brilliant mind to come to that conclusion, does it? Well, the second part of the first law is one that, if you think about, you will say, wow, that was the leap of faith there. Because it says an object in straight line motion at constant speed will continue in that manner unless acted upon by a net force. Well, let's break that down and think about that for a second. Have you ever experienced straight line motion at constant speed under no influence of a force? Maybe the closest you could come to it would actually be if you've been on a very, very slippery, smooth ice rink in which you're sliding along at a nearly constant speed because there's very little friction that slows you down. You're moving in a straight line. But even in that circumstance, there is friction, and you will ultimately come to a stop. So now imagine that we're talking about Isaac Newton existing and working in the early to middle 1600s, and making a statement like this, for which he essentially has no personal experience to inform him that this would be the case. In other words, under what conditions would he have ever experienced constant straight line motion under no net force and being able to determine that that motion would continue unabated until a force acts on him? We've had the luxury of seeing these laws validated by our astronauts as they have worked in space under very, very small or zero gravity environments, whereby they can measure and demonstrate that an object floating across the cabin of their space shuttle continues to float in a straight line unless acted upon by a wall or someone's hand, and so forth. So we have been able, in the latter part of the 20th century, to see the validation of Newton's first law. So you think about it, that makes this statement that much more amazing, that he would come to this conclusion based on experiments that others have done and his own thinking, that this was true, and to make the statement that this forms the foundation of what we mean when a force is present. They notice that the two parts of the statement actually tell us, yes, when a no net force is present, we would expect to observe an object to stay at rest or to continue moving in a straight line at constant speed. However, that also means that then when neither of those conditions are met, we know that forces are present, and so that is de facto the definition of when a force is present, we would expect to see acceleration occurring. In other words, the object is not moving at constant speed, but is now changing its speed and therefore is accelerating. So the first law, while deceptively simple, is brilliant. Now the second law, which follows on the first law, because the first law stated the conditions under which no net force existed, The second law says, now, if a net force is present, then the acceleration that is going to be due to that net force is related to it through an equation called Newton's second law, that the net force F is equal to the mass times the acceleration. In other words, if you divide the mass under the left-hand side, under the F, then you can say that when a force is present, net force is present, the acceleration that results from that net force can be calculated by dividing the force by the mass. Notice that the units of force, mass, and acceleration are as follows. Acceleration, we know, the units are meters per second squared. Remember 9.8 meters per second squared, the acceleration of gravity. We know the units on mass are kilograms. So those units, those fundamental units, combined together in the product mass times acceleration, result in the combined kilogram, meter per second squared combination. Now, in honor of Isaac Newton, we have renamed that grouping of fundamental units, the kilogram, meter per second squared, we've renamed that the Newton and given it the symbol capital N. So you may recall in chapter 3 when we were talking about vectors, we had an example of a force vector of 3 newtons in the x direction and 3 newtons in the minus y direction. So that's what that Newton unit meant. It is a combination of kilogram meters per second squared. In our English system, the unit of force is the pound. And this is the corresponding unit of force in the SI system. One place where we can use Newton's second law is to determine what we refer to as weight. Now, weight is the influence, the force of gravity on a mass. So some people misunderstand force and mass. In other words, you may think that if you go to the store and buy a pound of apples, that is a mass of apples. And in fact, that is the force of gravity on that collection of apples expressed in the pound unit. If you took those apples up into orbit, they would be essentially weightless. In other words, there would be no gravitational force on them. They would still be present. The matter would still be there. They would still taste like apples. And so having no weight does not mean there is no matter present. It simply means there's no gravitational acceleration acting on that object, and therefore we refer to it as weightless. So don't confuse the concepts of mass, which is the amount of matter present, and the concept of weight, which is the force of gravity on that matter. We can calculate the weight because essentially the Newton's second law, F equals ma, says that if you're in a gravitational environment where the acceleration a is given by the symbol g, and we'll use g from now on to indicate the gravity's acceleration of 9.8 meters per second squared. So if a equals g, then an object's weight is just the force F equals ma, or the weight W is m times g. So sometimes problems will be stated in which you're told how much a car or a train or a ball weighs. Maybe the car's weight is 20,000 newtons. Other times you may be told the car's mass, 1,200 kilograms. So don't confuse those two things. If you're given the mass, you may need to know the weight, calculate it using m times g. If you're giving the weight directly because it's expressed in newtons, then you don't need to know the mass in order to determine the motion of the object if you're just looking for net force. So this equation, W equals mg, is a useful equation for determining one of the forces that are acting on objects in a gravitational field. And weight is the force of gravity acting straight down on an object of mass m, and it's calculated by multiplying that mass m, expressed in kilograms, times the gravitational acceleration, and if it's on Earth, we're using 9.8 meters per second squared. So the first law expressed for us the conditions necessary for an object to be at rest or moving in a straight line under no net force. The second law expressed for us a relationship between acceleration and net force. The third law expresses for us the relationship between forces that act on objects and that come in pairs. Essentially, forces acting on an object are pairwise. And then stated as for every action there's an equal and opposite reaction. Notice that the box, in this case, the white box sitting on top of the blue box, which is blue box is sitting on the floor. Well, what are the forces going on here? Well, each box has mass. So the white box, because of its mass, is being pulled downward in the direction of the white arrow by a force of gravity. And we know what that force is. It's the mass of the box times g. However, that box is resting on top of the blue box, and the blue box must be pushing upward on the white box, essentially with a force equal but in the opposite direction, because the white box is at rest. And we already know that for an object at rest, the net forces must be zero. So you see here we have a white downward pointing vector and a blue upward pointing vector that when added together cancel each other out. And notice that if you think about the action would be the white box pushing on the blue box and the reaction of the blue box pushing up on the white box. So for each action there's an equal but oppositely directed reaction. Okay? And then if you think about the fact that the blue box, well, it's pushing on the floor. Of course, the white box's mass is included there, the mass of the blue and the white one now. So total mass of these two boxes is exerting a weight, downward weight on the floor, and the floor is pushing back with an equal and opposite force. Keep in mind that there's perspective involved here when you ask which force goes with which object. Notice that the white force is the weight of the white box. So that white force is acting on the blue box, but the blue box's force is acting on the white box. So these two forces are not acting on the same box. What about, consider this then, if you're standing on the picture of you standing here in the middle of the room. Are there any forces on you? I would hope you would say, yes, there are forces on me. Let's see, I have mass, therefore I have a weight. And my weight can be calculated by my mass times my acceleration of gravity 9.8. So I could draw a vector force representation of that weight sort of in the middle of my body, pointing straight down to the ground. Now, if that were the only force acting on me, then I would have to be accelerating in that direction. But I'm not. I'm standing in the middle of the room, so there must be another force acting in the opposite direction to cancel my weight. And that force, of course, is the contact force between my feet and the floor. In other words, the floor is exerting an upward force on my feet, and it's equal to the downward force of my weight. So that I'm not accelerating because there's no net force acting on me. And I could draw this as a single vector pointing straight up and equal in length to the one pointing down, but in the opposite direction. Now you would know that this is the case because if you think about the first law said an object at rest remains at rest unless acted upon by a net force. So if I'm standing in the middle of the room, I am at rest. I continue to be at rest. Therefore, the forces acting on me must sum to 0. So the first law tells me I know I have weight from the second law. The third law tells me I must have another force to cancel that, an equal and opposite one, because the first law says I'm not accelerating, I'm at rest. So you can see how you can use Newton's laws to analyze the situation. What if I remove the floor from underneath my feet? Well, I've removed the contact force, and since the contact force is gone between my feet and the floor, there's only one other force present. Gravity's still there. So now I have that non-contact force acting on my mass, accelerating it downward. So my state of motion is falling, and I'm speeding up because I'm under the influence of an acceleration. I know the value of that acceleration is 9.8 meters per second squared. So we characterize that motion by acceleration. We can measure it by measuring distance and time, and we can calculate from those distance and time measurements the velocity and the acceleration that is occurring. In terms of problem-solving skills and methods for working on force problems, the most useful way to approach problems dealing with forces is the method of drawing a free body diagram. The reason for this is that it takes any complexity out of the problem statement that may be confusing. In other words, if we were talking about a car, you might think, well, a car has 4 tires, and I've got to draw vectors between the tires and the car that point up, which represent the contact force between the tires and the road. And then the weight of the car, do I put that over the axles, 2 vectors down? Do I put it at the center of the car? What if there's, people in there? What do I do with those? And all of these questions simply add confusion to the situation. So we want to simplify that. We simply want to say, let's treat the object as simply, for instance, as shown here, a box, a square. Could be a sphere, could be a circle, whatever. Just treat it as an object. Take away any of the complexity of that object and say, if this were my car, represented by this box, what forces are acting on it? And draw those forces in the direction they're going as if they're passing through the center of mass of the object, and through the center of the object, if you will. So notice in this particular diagram we have a couple of little purple vectors, one pointing down, one pointing up, passing right through the center point of the object. I have a black vector pushing to the right and a red vector pushing to the left. And all those do is represent to us the forces acting on this object. So we want to remove the complexity and only focus on what are the forces, apply them to the object, and then ask the question, well, is there anything left over between the black vector pushing to the right and the red vector pushing to the left? It kind of looks like there's a little more right than left, and therefore there's going to be a net force on this object to the right. The two purple vectors look like they're going to be equal and opposite, and so that's not going to result in any net force in the vertical direction. So drawing free body diagrams is a good way to reduce the complexity of the situation and get to the heart of the matter. That is, what are the forces acting and which way are they pointing? Here we see an example in which we have an object that's being supported by a rope in an overhead hoist. And we're told that the object, the rope can withstand 400 newtons of tension. In other words, if we hung something on this rope that weighed more than 400 newtons, the rope would break. Okay. Now we're going to accelerate this mass upward with this rope on this hoist, meaning the hoist is going to start up and speed up. The object is going to rise up at an increasing speed. And we would like to know, what is the maximum acceleration that this hoist can go at so that the rope is still able to support the mass? Okay, 25 kilogram mass will be the mass we're going to actually lift up vertically. Well, I've drawn the free body diagram on here, and you'll notice that we're saying that the rope is exerting a force on the mass, represented by the white vector and the labeled F rope, F sub rope. And the weight of the object is the red vector downward, labeled by W. So those are the two forces acting on this mass. If you think about it, think about an object being suspended by a string and saying, what are the forces acting on the object? The string is pulling up and gravity is pulling down. Okay? That's all we're representing here. The vector A, shown beside the box, is the direction in which the mass is accelerating. It's accelerating because the force of the rope is greater than the weight, and so we have a net upward force. So notice we've listed to the right the calculation and the identification of the 400 newtons is the maximum force the rope can withstand, so we're going to put that in because we want to know what acceleration corresponds to having that maximum force. The weight of the object being 25 kilograms times 9.8 meters per second squared calculates out to 245 newtons. The acceleration that the object can safely attain is the net force divided by the mass. Well, the net force is 400 up, 245 down, or a difference of 155. And 155 divided by the mass m, 25 kilograms, is 6.2 meters per second squared. So this would be the limit. In other words, this is as much acceleration as you can apply to this mass and rope system and still have the rope not break. So notice that drawing the free body diagram allowed us to see visually the net force being the difference between the rope force and the weight. And then notice over in the calculation A equals F net over M. F net in particular is the sum of all the force vectors that are acting on the object. Well, we only have two, 400 up, 245 down. So the net force is a mathematical combination of those. Okay. Now here's another example. An object with a mass of 4 kilograms travels 4.8 meters per second northward. It is acted upon by another force of 6.5 newtons, which is directed in the direction of motion, which means north, doesn't it? And another force of 9.5 directed in the opposite direction, south. And both of which are continuously acting and applied to the object. So even if the object were momentarily to stop, do not remove the forces from it. Okay? An example of that would be this. What if you threw an object up in the air? The object slows, steadily slows, comes to a momentary stop at the peak of its trajectory, and then falls down again. Did the force of gravity get removed at any point along that path? No, it didn't, did it? Okay, so that's what I mean by don't assume that because the object stops its velocity that the forces are gone. Okay, we want to know two things here. How far will the object travel before coming to rest? In other words, because of these forces, it's going to slow its velocity and stop momentarily. And we ought to know where will that occur. And then what will its position 2.5 seconds after that? Where is it located? Well, notice what we've labeled here. In our knowns area of our template, we've placed the mass that we know, 4 kilograms. We've placed our original speed of 4.8 meters per second. And we've labeled our two forces, 6.5 in one direction and 9.5 in the other. Okay? Now, this is a one-dimensional problem, which is nice. We don't have to worry about x's and y's. This is just occurring in a straight line. The mass m is traveling along the direction of v, 0, slowing down because there's a greater force against it than there is with it. So it's decelerating. In other words, its velocity is decreasing. As its velocity decreases, ultimately its velocity decreases to 0. We want to know at what time that occurs, where it is. And then those forces are still present, so now that downward force is greater than the upward force, then it is now taken over, and so now we have a net force acting in the other direction. We did before, but now we're moving in the other direction. And we'd like to know where will it be 2.5 seconds after it momentarily stopped. So let's use the direction x as our variable. We know that we want to solve for the position x when the velocity goes to 0, right? When it goes to momentarily at rest. Well, the equations we're going to identify that we want to use involve x. Notice that the first equation, x equals, is the format. And the second equation, there's an x there on the right-hand side, which we could rearrange and solve that for x. In either one of these formulas, we need the acceleration. Now you see that the kinematics equations that we've used before were represented here. We were often given the acceleration. Now we have enough information by forces and mass to calculate the acceleration which we can then put back into our kinematics equations. So just to sort of close the circle here, that's why I said in the introductory material that this stuff is cumulative, isn't it? In other words, you still need to know the kinematics here because now you're using the dynamics equation, Newton's second law, to solve for acceleration and then put it back into kinematics expressions from the previous chapters. Well, anyway, use the second law. What is the net force? We had 6.5 newtons up, 9.5 newtons down. Or 6.5 newtons in the positive direction, 9.5 newtons in the negative direction. It means we have a -3 net force. That -3 net force is applied to a 4 kilogram mass, which results in an acceleration of -0.75 meters per second squared. In other words, the acceleration is negative opposite to the velocity. Okay? The acceleration is acting against the velocity. Take that acceleration and plugging it into our v squared equation. And you've seen the information that we are looking for where the object attains a zero velocity. So v squared is 0. v0 squared is our 4.8 value, the initial velocity, and 2 times a -0.75 acceleration times x. And there we go. We've solved for x. We find out that 15 meters away from the origin, the object has now come to a rest momentarily. Remember, the net force of -3 newtons is still present, so it's not going to stay at rest because there's a net force on it. It's going to accelerate at 0.75 negative in the opposite direction. So where will the object be 2.5 seconds later? Well, we know it's 15 meters from the origin. It's accelerating back toward the origin at -0.75. And so we can go ahead and use our kinematics equation, x equals v0t plus 1/2 at squared. Now recall that in this case, v0, we are at rest momentarily at this position 15 meters. So we'll just treat that as our origin and have zero velocity. And 2.5 seconds will go into our equation in the t squared area with our -0.75 meters per second squared acceleration. And we'll calculate that from that point where we stopped, we will go back 2.3 meters in 2.5 seconds. And so if we realize that we went out to 15, we've come back 2.3, so that leaves us roughly 13 meters from our starting point, 12.7 to be exact. Now in that problem, we were dealing with two forces that were collinear, meaning they were on the same line. The 6.5 in one direction and opposite to it, the 9.5. Well, not all forces are going to be collinear. We call these non-linear forces. Since forces are vectors, we will have to treat them as vectors, and as such they may be pointing in all directions, and we will have to figure out how much force is pointing right and left and how much force is pointing up and down. So we're going to have to be able to add vectors, subtract vectors, manipulate vectors in order to determine the subsequent motion. Let's do some problems here. First of all, what is the mass of an object on the surface of the Earth where the acceleration is 9.8? If this object's weight is 100 newtons, well, as you can see, we've been given the weight. We know the weight is related to the mass through mg. Rearrange that, solve for the mass, which is the weight over the gravitational acceleration, give 10.2 kilograms. Simple calculation. What about this? When you sit on a chair, what is the resultant force on you? Is that a new word? Resultant is what is left over when you've added up all the ups and downs, rights and lefts. It's the net force, isn't it? So the net force on you is 0. It doesn't depend on your weight because you weigh more, but then the chair is pushing back more against you. So you have equal and opposite. Newton's third law. How about this one? Starting from rest, a 4 kilogram body reaches an 8 meter per second speed in 2 seconds. What is the force acting on it? Well, what's happening to this object? We see that it starts from rest, meaning 0 meters per second. It reaches a final speed of 8 meters per second, and it does that in 2 seconds of time. So go back to your definition of acceleration, which is the change in velocity over the change in time. So our velocity has changed from 0 to 8, so it's changed by 8 meters per second, and it's done that in a change of time from 0 to 2, or 2 seconds. So 8 meters per second in 2 meters per second is a 8 over 2, 4 meter per second squared acceleration. So an acceleration of 4 meters per second squared for an object of 4 kilograms means that the force had to be 16. 4 kilograms m times 4 meters per second squared a. F equals ma. You can pause this to examine it more closely at your discretion. Now here's an example of two forces which are not collinear. They don't act along the same line. We have a force of 8 newtons acting in the y direction, essentially, vertically, and a 6 newton force acting in the horizontal direction on a 5 kilogram mass. Notice in the problem statement the question mark occurs for the statement, what is the acceleration of the mass? We're looking for A. We've been given the mass, we've been given the two force pieces, and we'd like to know, based on those two force pieces and the mass, can we find the acceleration? Now remember that in order to use F equals ma as an equation for determining magnitude of force and magnitude of acceleration, we need to be able to put in a single number for the force and the mass and calculate a single number for the acceleration in order to get the magnitude of the acceleration. Well, this force being comprised of two pieces, we need to express it as one piece. If you think about it, those two pieces, those two perpendicular pieces, 6 and 8, are the two sides of a triangle whose hypotenuse is the square root of 8 squared plus 6 squared. 8 squared is 64, 6 squared is 36, sum of those is 100, so the square root of 100 is 10. So a 10 Newton force acting at an angle sort of upward and to the right at a 53-degree angle is the same as a force of 6 pulling to the right and a force of 8 pulling vertically. So we know we have a 10 Newton force applied to a 5 kilogram mass, which will result in an acceleration of 2 meters per second squared. And the angle of that force is the angle at which the acceleration will occur. 53 degrees north of the east direction. Here we see a representation of a traffic light being supported by two wires. The wire is making 37-degree angles with the horizontal direction, and two wires, meaning that we really have two forces pulling off in the upward direction to the right and to the left. Notice the green vectors, one pulling up to the right and vertical, and one pulling off to the left and vertical. The other force is the weight of the traffic light acting straight downward. This is our free body diagram for this object. Three forces acting on the light. Now we need to figure out the amount of forces acting vertically and the amount of forces acting horizontally on this traffic light. If you think about it for just a moment, you will realize that the forces acting horizontally, the portion of the wire pulling to the right and the portion of the wire's force pulling to the left, they must cancel each other out. And then each wire contributes an amount of force upward, so those two pieces must equal the downward weight. It looks like this. We refer to the tension in the wire as capital T. The tension in the wire can be expressed as the vertical component, T times the sine of theta, and a horizontal component, T times the cosine of theta. Each wire will have a vertical component, T sine theta, pulling upward. So the table shows T sine theta under the Y value for one wire, T sine theta under the Y value for the other wire. The table shows under the X direction, T cosine theta, portion pulling to the right, and then the left-hand wire, negative T cosine theta, pulling to the left. So in the X direction, those two pieces sum to 0. But in the Y direction, those two pieces sum to 2t sine theta. Now, since the light isn't moving, we know that the upward net force has to also be 0, so as much force is pulling up as is pulling down. And so we have 2t sine of theta, theta is 37 degrees, so 2t sine 37 up minus the weight of the light bulb down, 100 newtons, the traffic light, and those two pieces have to sum to 0. And notice that the only unknown left there is t. We can solve that for t and find that the tension in the wires is 83 newtons. We would do this because we want to design in a safety factor and say, what material do we need to use to make sure that those lights are supported, and then build in a multiplying factor of, say, okay, let's use a material that's at least 2 or 3 times stronger than this, and then we're good. Now, one of the forces that we can model very easily is the force of friction, and so we want to include that as another one of the forces that we're going to use in solving problems. Friction is a difficult force to quantify because it involves the interaction of microscopic irregularities in surfaces and micro-welding that occurs between surfaces that are in contact. And therefore, because that's very complex, and you think in terms of how many possible irregularities could be interacting between the upper and lower surface in any square centimeter of surface area, it may be billions and billions of interactions. And so from what we refer to as first principles, it would be a difficult problem to solve. However, from an experimental standpoint, what we refer to as empirical evidence, we can develop a relationship by seeing how difficult it is to move one object over another object, slide one object over another object, by measuring the force it takes. And then relating that to the amount of normal force that is exerted between the two objects, we can come up with a coefficient of friction that relates to the difficulty with which these two objects have in sliding over one another. This empirical relationship is listed here. It says that the frictional force, lowercase f, little f, is equal to the coefficient mu. That little u with a tail on the front side is the Greek letter mu, the lowercase m in the Greek alphabet. And that's our coefficient of friction. And then times the normal force. The normal force is the force with which the surface is pushing back on the object that's resting on it. So this is a way of expressing frictional force, and we can include this in our force expressions that we use when we're calculating Newton's second law. As I said, we determined the coefficient of friction by actually measuring how difficult it is, what force we have to apply to an object to slide it over the surface of another object. On a level surface, the normal force is the weight of the object resting on that surface. In other words, the weight of an object pushing down is being reacted against, according to Newton's third law, by an equal and opposite force pushing up. So if you're pushing down with a weight of mg, the surface is pushing up with what's known as a normal force, given by the same value mg in the opposite direction. The word normal is used not to differentiate it from, say, abnormal or weird in somehow, but to normal meaning perpendicular to the surface. So on a level surface, the normal force is pointing straight up, whereas the object sitting on it, its weight is pointing straight down. Some examples of static from coefficients of friction are shown here. Now, there's a graph in your textbooks that shows the force of friction actually increases as you approach an object beginning to break free and move, and then once it breaks free and moves, the force of friction actually reduces. Now, the reason for that broadly is that once an object is moving, the irregularities that it encounters and the micro welds that may have formed are broken, and the object has momentum at this point, and so that it's easier to keep moving than it was to start moving. So that an object, once it's moving, actually has lower friction on it. Once it's sliding, there's lower friction acting on it than when it was at rest. And you can see that for wood on wood, the coefficient of friction for when an object is at rest, it's 0.06, is higher than the coefficient when it's moving, 0.04. So we call these two different coefficients static and kinetic. Where static is the one where the object is not moving, it's always higher than the kinetic coefficient for when the object is moving. Notice that rubber tires on dry concrete have a coefficient of 1.2 when they're at rest, and then when you're skidding, you've locked your tires and you're skidding, the coefficient is actually lower at 0.9, which means that you will actually take longer to stop if you've locked your tires and are skidding than if your tires are rolling. Because when you're rolling, the surface of the tire and the road are actually not moving relative to one another, and you have a higher coefficient of friction. That's the basis behind anti-lock brakes. You will stop faster if your tires continue to roll rather than slide. Here we have a 200 kilogram car moving and comes to a stop in 25 seconds. We would like to know the value of the static coefficient of friction. We have 1,200 kilograms, kilograms for its mass. Its velocity was stated as 100 kilometers per hour, which we need to convert that to meters per second. Remember, our units are always kilogram, meters, and seconds. And the time is in seconds. Notice our free body diagram over there. We've really only shown on that diagram that the force applied to the object in the horizontal direction is the friction force. And we haven't bothered to show the downward weight or the upward normal force because we already know that those on a level surface are going to be equal and opposite. But at any rate, what we're trying to calculate is the coefficient mu in this case. And mu is related to the force of friction and N by the ratio F over N. Well, that means we need to find out what are we going to put in for N. Oh, that's right. N is the normal force, and for a level surface, the downward weight is equal and opposite to the normal force. So N is equal to mg. Now remember that this mass m is obeying Newton's second law. Newton's second law says the net force is equal to mass times the acceleration. Well, the net force in this case is only the friction force acting against the velocity. So we substitute little f in for capital F, and we have little f equals ma. Okay? So we can then replace mu equals F over N. We can replace little f by ma. We can replace N by mg. Notice the m's cancel out. We can substitute for A, our defining equation for acceleration, which is change in velocity over change in time. Substitute that in for A, and we get an equation symbolically that says the mass times the change in velocity over the time divided by mg is mu. And when we plug in our numbers, we find we get 0.113 as our coefficient of static friction in this case. As I mentioned earlier, static friction is the one that's important for a car tire on a road because it's the higher value of the frictional force than the sliding friction, which is the kinetic coefficient. And if you think about it for a moment, to revisualize the rolling of the tire over the surface of the road, the point of contact between the tire and the road is not moving. In other words, there's not sliding when you're rolling. And so that means that the point of contact and the road are at rest relative to one another as the tire rolls over the surface. And so you have a higher coefficient of friction than if the tire were sliding and not rolling. So here are some problems that you might want to look at and see how you'd apply Newton's second law to these situations. For instance, in this first problem, we have two people pulling. We are told that the rope has a certain mass. So the rope is the thing being acted upon, isn't it? Sue pulling one way, Sean pulling another way. And as a result of their two forces, they have a net force that results in the mass accelerating with a 2 meter per second squared acceleration. So do that problem. Here we have an example of a coefficient of friction. And we're told that the coefficients of friction are 0.4 and 0.3. Okay? Now we're going to apply a net force of 15 newtons to this box. And we're going to ask the question, what is the net force on the box when a 15 Newton horizontal force is applied to the box? Okay. Well, first of all, we have to ask the question, if we apply 15 newtons of force to this box, what is actually going to occur? In other words, we know there's friction. Is this enough force for the box to move? Well, how much force does it take? Well, if we want to get the box to move, we have to overcome the frictional resistance. The frictional resistance is calculated by the coefficient of static friction times the normal force. Well, the coefficient of static friction is 0.4. And the normal force is the weight of the box, which is 3 kilograms times 9.8 meters per second squared, which is 29.4. And so that's pretty close to 30, isn't it? So 0.4 mu and n is 30. 0.4 times 30 is 12, isn't it? So we have enough force with 15 newtons to overcome the 12 newtons of resistance. So it will start moving, won't it? You might say, okay, well, 15 minus 12 is 3. I don't see that answer there. The reason for that is, once it's moving, we know that the kinetic coefficient is the one that we have to deal with. And the kinetic coefficient is 0.3. So once it's moving, the resistance is actually less than the 12 we originally calculated. In other words, the resistance is now 0.3 times approximately 30 newtons of weight. 0.3 times 30 is 9. We're applying 16, and we're being resisted by approximately 9. So that means that, in fact, the net force on the box is approximately 6, or D. Knowing the net force, knowing the mass of the box, we would know the acceleration. Knowing the acceleration, we would know the position velocity at any time. Similar problem, an object slides on a level surface and comes to a stop. The only reason it comes to a stop is because friction is present. Friction is acting to slow it down, just as in the previous problem that we had done. And you can calculate the coefficient of friction based on knowing what is the acceleration of the object and the idea that it comes to rest. Same thing here. This is a situation where a puck has an initial velocity. It travels a certain distance, comes to a stop. And we can calculate the coefficient of friction that's acting on the puck. Once again, we have a box here sliding over a horizontal surface being pulled by a force. But in this case, the force of 5 newtons is being resisted by a frictional force of 3 newtons. So we know that there's a net force of 2 acting on this box. What would be the acceleration resulting? This is a problem involving an inclined plane. Now the only difference here is that now the object sliding down an inclined plane, the object has a weight which acts normally straight down, okay, but the plane, the surface it's in contact with, is not parallel to the ground. It's inclined slightly. Therefore, the reaction force of the surface pushing perpendicular to that surface against the object is less than the normal force we calculate on a level surface. And so we'll have to deal with this next time as we do some applications of Newton's laws. But I wanted you to see that we can deal with this situation. We will be able to calculate it. We just will have a reduced value of our normal force. So as you go through these problems, take a look at these problems, and we will discuss them in our chat rooms and via email, and we'll be able to apply Newton's laws, in particular Newton's second law, F equals ma, to all of these situations. Thank you.